Hello, I'm Uzi Hanafis from Department of Electrical Engineering at Lahore University of Management Sciences, Pakistan. In this video, I shall be talking about my work, Differential and Weighted Slepian Concentration Problems on the sphere. This is the outline of my talk. After providing an introduction of the topic, I will present the mathematical background, followed by a detailed discussion of the differential and weighted Slepian concentration problems. Then I shall demonstrate the usefulness of the proposed work through some applications before I present the concluding remarks. So without further ado, let's start. The uncertainty principle states that it is not possible for a signal to have finite support in the time domain and the frequency domain simultaneously. In other words, a function that is strictly limited in the spatial or temporal domain has an infinite support in the spectral or frequency domain and vice versa. You may say that a function that is band limited is never local, strictly speaking. However, it is possible to find the maximal concentration of a function in a particular region of one domain while it is strictly limited in the other domain. So we try to find an optimization of those constraints of band limitation and space limitation. The problem of finding band limited functions with some optimal spatial concentration is known as the Slepian concentration problem, and it was first proposed in a series of classical papers for the one-dimensional time-frequency domain. The set of functions that we get from this problem are called the Slepian functions, and they exhibit a lot of interesting properties and thus have found a wide variety of applications in several diverse fields of science and engineering. The wide applicability of the one-dimensional time-domain Slepian functions motivated researchers to extend this concept to higher dimensions, for example, the two-dimensional Cartesian plane and other geometries in the Euclidean setting. Furthermore, the spherical analog for the one-dimensional Slepian concentration problem was proposed for applications related to curved surfaces, and it is herein referred to as the classical Slepian concentration problem on the sphere. The resulting Slepian functions have been utilized for applications in geophysics, cosmology, geodesy, acoustics, planetary sciences, signal estimation, spectral analysis, hydrology, graph theory, etc. So in this work, we present a generalized formulation of the Slepian concentration problem on the sphere for finding band-limited functions with an optimal concentration in the spatial domain. By introducing weighting functions in the formulation of the classical Slepian problem and assigning different values to those weighting functions, we present two variants of the concentration problem, namely the differential and the weighted Slepian concentration problem. In the differential Slepian concentration problem, we consider two regions on the sphere and find band-limited functions such that the energy is maximized in one region at the expense of energy in the other region. In the weighted Slepian problem, we propose non-negative weighting as a spatial window function to obtain the Slepian functions. We solve each problem by formulating it as an eigenvalue problem in the harmonic domain. The solution yields eigenfunctions that serve as an alternative basis functions for the representation of band-limited signals and are referred to as the Slepian functions. We also present and analyze the properties of the proposed Slepian functions. To support the applications in acoustics and cosmology, we also provide a demonstration for the use of the proposed Slepian functions for the robust signal modeling and the estimation of energy spectrum of red and white stochastic indices on the sphere. Let us now familiarize ourselves with the mathematical background needed to understand this work. A unit sphere denoted by S2 is defined as given in equation 1, where U hat denotes a vector in the 3D Euclidean domain. In the spherical coordinate system, a point on the unit sphere is described using two parameters, namely the co-latitude theta between 0 and pi and longitude phi between 0 and 2 pi. We consider complex-valued square integrable functions on the unit sphere which form a complete Hilbert space denoted by L2S2. For any two functions f1 and f2 defined on the unit sphere, the inner product associated with this space is given in equation 2, which induces a norm presented in equation 3. The spherical harmonic functions or the spherical harmonics form a set of complete basis functions for the Hilbert space L2S2 and are defined by the equation 4, where L is the angular degree and M represents the angular order, and PLM of U denotes the associated Legendre polynomial of degree L and order M. With the adopted definition, the spherical harmonics are orthonormal, as given in equation 5, where delta LL dash represents the Kronecker delta. Due to the completeness of the spherical harmonic basis functions, any signal f theta phi defined on the sphere can be represented in the harmonic domain using the spherical harmonic transform. In equation 6 and 7, the quantity FLM represents the spherical harmonic coefficients of degree L and order m. A signal f in L2S2 is said to be space limited within the spatial region R if it has the following form as given in equation 8. A signal is said to be band limited at L if the spherical harmonic coefficients FLM equal to 0 for any L greater than or equal to capital L and can be expanded as given in equation 9. The subspace of band limited functions is denoted by HFL and it has dimension L square. We use the vector notation F to represent a column vector of length L square containing spherical harmonic coefficients as given in equation 10. The spatial and spectral representations of the signal are related through isomorphism. Using the Parseval's theorem, we can find the total energy of a function f on the sphere in terms of its spherical harmonic coefficients, as well as the cross energy of two functions f1 and f2. Now that we have reviewed the mathematics, let us come to the main problem. In this section, we revisit the Slepian concentration problem for signals on the sphere and present a generalized framework and the variations of this concentration problem. We define the generalization of the Slepian concentration problem of finding band-limited functions f in the subspace HFL as the ratio of the weighted inner products of f. Here, HU and GU represent the weighting functions and lambda is the ratio of the weighted energies. Equation 14 represents the spectral domain formulation of the problem. By defining coupling matrices H and G, we may write this problem in the matrix form as given in the Rayleigh quotient here. The classical Slepian concentration problem refers to finding band-limited functions with optimal concentration in some region R on the sphere. The region R may be a single connected region or a union of disjoint subregions RA, RB, etc., with area represented by R modulus. Equation 15 represents the spatial domain weighting functions of the classical Slepian problem, where I, R, U hat represents the indicator function of the region R. Solution of this problem yields a family of L-square mutually orthogonal eigenfunctions, which we call the classical Slepian function. Due to the optimal localization and the orthogonality of the classical Slepian functions over the region R, they have been used in numerous applications. We now present the first variation of the Slepian problem, where we counterbalance the energy concentration between two regions, say R1 and R2, such that the energy in one region is enhanced at the expense of diminishing energy in the other region. For this variation, we define the weighting functions given in equation 16. The differential Slepian concentration problem can be written in the spectral domain form as the Rayleigh quotient presented here. The matrix H is a difference of two matrices 1D and 2D, where D is represented by equation 17 and is the coupling matrix representing each of the regions. The solution F that maximizes lambda in the Rayleigh quotient is also a solution of the eigenvalue problem HF equals to lambda F. Since H is Hermitian symmetric, the solution of the eigenvalue problem yields a set of L-square real eigenvalues and L-square orthogonal eigenvectors. Their orthogonality is presented in equation 18. Equation 19 represents the eigenvalue problem in spatial domain. Each spectral domain eigenvector f alpha relates to the spatial domain eigenfunction f alpha of u hat, which we refer to as the differential Slepian functions. The eigenvalue lambda alpha quantifies the difference in the energy concentration of the eigenfunction f alpha over the regions R1 and R2. When eigenvalues and the corresponding eigenfunctions are indexed in non-increasing order, then the differential Slepian function f1 of u hat associated with the largest eigenvalue is the function with maximum energy concentration in the region R1. On the other hand, the differential Slepian function f(L square of u hat associated with the smallest eigenvalue is the function with the maximum energy concentration in the region R2. Let us now analyze the properties of the differential Slepian functions. First, we will discuss the orthogonality property. The differential Slepian functions are orthonormal over the sphere. but orthogonal over the regions R1 and R2. However, the differential Slepian functions are nearly orthogonal over region R1 as given in equation 20. Similar results hold true for the region R2. The cosine of the angle between any two differential Slepian functions can be computed as presented by equations 21 to 23. The proof of these relationships can be found in Appendix A. Interesting property is that the differential Slepian functions form a complete basis for the space H of L. In this next property, we study the spectrum of eigenvalues. Since H is Hermitian indefinite, we choose the eigenvalues to be between +1 and -1. The quantity n of H represents the Shannon number for the differential Slepian concentration problem, and it is equal to the difference of the trace of the coupling matrices 1D and 2D, and it is shown to be equal to the product of the bandwidth and difference of the area of the regions. The last property is that we analyze the symmetry of the solutions. Since 1D minus 2D equals to negative of 2D minus D1, the solution of the original problem holds with just an inversion in the signs of the eigenvalues. For the differential Slepian concentration problem, we provide an illustration and analyze the eigenfunctions, spectrum of eigenvalues, orthogonality properties, and energy enhancement enabled by the eigenfunctions over the region of interest. We use the following parameters. Bandwidth L equals 16. R1 and R2 are taken as north and south polar gaps respectively. In this figure, we have plotted the differential Slepian functions over the sphere. Plots A to F show the real and imaginary part of the first 6 most concentrated Slepian functions in region R1. Plots G through L show the real and imaginary parts of the last 6 eigenfunctions. As expected, they are concentrated in the region R2. We also analyze the spectrum of eigenvalues. In figure A, the two phase transitions are visible which are associated with the two regions. The negative and positive eigenvalue spectra are plotted in figure B. The dashed lines show the Shannon number n1 and n2 associated with the eigenfunctions obtained from the solution of the classical Slepian problem on the regions R1 and R2 respectively. To analyze the mutual orthogonality of the eigenfunctions over the spatial regions of interest, we compute the inner products of these eigenfunctions as well as the bounds. In this figure, the top row shows the actual inner products and the lower row shows the bounds on the inner products. The differential Slepian problem yields eigenfunctions which have increased energy in the region R1, while energy in the region R2 decreases. We illustrate the latter by comparing the energies E subclass and E subdiff in the region R2 when the classical and differential Slepian problems respectively are implemented on the sphere. As seen in this figure, the energy of the Slepian functions in the region R2 when the differential Slepian method is used is less than the energy of the eigenfunctions when the classical Slepian method was used. The two regions R1 and R2 associated with the differential Slepian problem can have any arbitrary orientation on the sphere. If the two regions are located as shown in this figure part A, then they are categorized as rotationally symmetric around some axis V1 hat and antipodal regions. If the regions are located such that their axis of symmetry is aligned with north or south pole, then they are known as azimuthally symmetric antipodal regions, as can be seen in this figure part B. The formulation of the differential Slepian concentration problem in case of azimuthally symmetric regions is significantly simplified. For azimuthally symmetric region R of K, the formulation of KDLL-MM- is simplified by exploiting the orthogonality of the complex exponentials along the longitude. This arrangement greatly reduces the computational burden of the algorithm since now you're solving eigenvalue problems of a smaller size, that is L minus M cross L minus M, instead of the size L square. Now we present the second variant of the Slepian problem, which is the weighted Slepian concentration problem. We choose the weighting functions as given in equation 25, and we see that h of hat is a real non-negative function which is bounded by unity. For the choice of weighting function, we solve the Rayleigh quotient. Since h is positive semi-definite and Hermitian symmetric by definition, all the eigenvalues of h are real and non-negative, and the corresponding eigenvectors can be chosen as orthonormal. For each eigenvector f alpha, we have a corresponding spatial domain eigenfunction f alpha u hat, which we refer to as the weighted Slepian function. Here we analyze the properties of the weighted Slepian functions. The weighted Slepian functions exhibit threefold orthogonality. Firstly, since the eigenvectors are orthonormal, the eigenfunctions are also orthonormal by isomorphism. Secondly, the eigenfunctions display spatial domain orthogonality with respect to a weighted spatial domain inner product, as given in equation 27. And finally, the eigenfunctions are orthogonal with respect to complementary weighted inner product. After having discussed all the mathematical framework underlying the proposed variants of the Slepian problem, we are now ready to demonstrate the usefulness for localized spectral estimation and signal modeling. The band-limited differential Slepian functions serve as a good choice for localization functions due to their optimal spatial concentration and orthogonality properties. For a global function p, we obtain its localized version using the differential Slepian function fu hat as in equation 29. We assume that the function p has isotropic energy spectrum. Let the localized energy spectrum be represented as S psi psi. Then the relationship between SPP and the expected value of S psi psi is given in equation 30. To illustrate the effectiveness of the differential Slepian functions as the localization window functions, we estimate the white and red stochastic processes on the sphere. The energy spectrum of various stochastic processes follows the power law given by equation 31. Using the same parameters as before, that is L equals 16 and R1 and R2 taken as north and south polar caps respectively, of radii pi by 6 and pi by 8, we obtain the estimate of the energy spectrum for white and red process. Using the first 6 most concentrated window functions seen in the previous slides, it can be seen that the localized estimate supports the global spectra for both white and red processes. Just as the classical Slepian functions, the proposed weighted Slepian functions also serve as an alternative basis functions for the representation of band-limited signals. Using the orthonormal weighted Slepian functions, any band-limited function g can be expanded as given in equation 32, where the coefficients g alpha and gh alpha are defined as given in equation 33. In this talk, we presented a generalization of the Slepian concentration problem on the sphere by introducing weighting functions in the formulation. We have presented two variants, namely the differential and the weighted Slepian concentration problem. The differential problem considers two regions on the sphere and maximizes energy concentration of a band-limited signal in one region while it is minimized in the other region. On the other hand, the weighted concentration problem uses non-negative weighting as a window function for the localization of signal energy. Each of the problem was formulated as an eigenvalue problem in the spectral domain. The solution of each problem yields eigenfunctions, referred to as Slepian functions, that serve as alternative basis functions for the representation of band-limited functions. We not only presented and analyzed the properties of the proposed Slepian functions, but also demonstrated their usefulness for signal representation, localized spectrum estimation, and signal modeling to support applications in cosmology, geophysics, acoustics, and beyond. Thank you.